Good morning, students. We're going to take a look at today's lesson. We're going to be looking at 7.5. It's entitled Areas of Regular Polygons. So we're really going to be talking about just a couple formulas that you want to get down and then a couple of concepts. Now this concept can be a little tricky if you're not careful, so make sure you're paying close attention to the slides and to the work that we do. Circles can be inscribed in a circumscribed about a regular polygon. If you look at the picture here that you guys see here, this picture that the arrow is drawn to, you can see three different shapes. You can see a small circle, the green circle, then you can see the triangle, and then you can see the large blue circle. The green circle is something that we would say inscribed because it's inside the triangle. The blue circle is called circumscribed because it's around the triangle. What we're going to be looking at today primarily revolves around polygons that are inside of, or circles inside of polygons. So we're really going to be referring to inscribed and both circumscribed at the same time. The centers of the inscribed and the circumscribed centers are the same point. The common center of the concentric circle is called the center of the regular polygon. So that dot that we see right here, point C, it's called the center of the polygon, which in this case is the triangle, and the center of the two circles. Concentric means they both have the same center. So if you think of a bullseye, how it has multiple circles and it has one center point, that's the example of what inscribed and, the concentric circles are. Okay, so the radius of a polygon, now this is a very important component here because again, you can see this polygon on the screen right here. We have 5 sides, so we know it's a pentagon. You notice that you can break any kind of polygon into triangles. We've already talked about this. The term we used was triangulation. So always remember that the number of sides on the polygon will always be equivalent to the number of triangles that you can make inside the polygon. So you count up the number of sides, there's 5, and then that means that we can draw 5 different triangles inside. All these triangles are congruent by the side postulate, and there's several things that we've got to point out about this particular shape. The radius of a regular polygon is the segment that joins the center and the vertex of the polygon. So here's the center, and then here's one of the vertices of the polygon, and then you see this line right here that connects the two. That's referred to as the radius of the polygon. Now we got to remember the term regular polygon. Regular again means that the angles are all congruent, all the anterior angles, and all the length of the line segments are congruent. So all of these line segments are congruent, and we know that the interior angles are also congruent. That's what the term regular means. So we can't forget that. That's actually very important for this lesson. The central angle of a regular polygon is the angle formed by two radii drawn to consecutive vertices. So we can look at this triangle right here that's drawn. There's one radius, and here's another radius of the polygon. And the central angle is that angle in the very middle. Now this is actually a very important angle in this particular lesson, but whenever you hear the term or read the term central angle, that's the angle that it's referring to. The apothem of the regular polygon is the perpendicular segment that joins the center with the side of the polygon. It's given the letter A. I'm drawing an arrow to it right there. That is the apothem, that green dotted line. Now that's actually going to be important toward the end of the lesson because that's going to be used in one of the formulas that you have to write down on your formula sheet. So the apothem, if you connect a line straight from the center of the circle to the opposite side, it will give you the apothem. All right, find the following angle measure in the regular octagon, and then the measure of the central angle. So we're looking for the measure of this angle right here. And I'm trying to draw here with my pen, and it's not letting me do this. So we have to find the measure of the central angle. Well, if you guys hopefully are sharp enough to understand that if I were to draw a circle inside of this, that we know that there's 360 degrees in a circle. So what I'm basically doing is I'm taking just a very small section of that, and that's going to be what the central angle measures. So you see the formula on the screen here, the 360 divided by 8. Now 360, again, 360 degrees in a triangle. I'm sorry, 360 degrees in a circle. And then I need to divide that by the number of triangles that I have. Since this is an octagon, which is 8 sides, I know there's 8 triangles in the octagon. So to find the measure of the central angle, it's simply, there's a formula. You could write this down if you'd like to. You could entitle it central angle on your formula sheet. It's simply equal to 360 divided by n. And n is the number of triangles or the number of sides that you have in the regular polygon. Since an octagon has 8 sides, that's why we have the number 8. So 360 divided by 8, that will give me the measure of the central angle, which in this case would give us 45. So the central angle here measures 45 degrees. The measure of each base angle in the triangle form consecutive radii. So here, talking about the base angle, these are the base angles that it's referring to here. The base angles, the measure of each base angle in the triangle forms consecutive radii. So you see the formula on the screen here, the measure of angle P plus the measure of angle PRQ and PQR have to equal 180 degrees. I'm marking them all right here for you, and we already know this theorem. We've been talking about this for quite some time. So the sum of all the angles in a triangle have to be 180 degrees. And the measure of angle P and Q have to equal P and PQR and PRQ have to be congruent. And the reason we know that is because we know that all radii, which those are the radii of the polygon, are congruent. So since the radii are congruent, the angles opposite of them also have to be congruent. So that's how they set that up. So they say 45. The 45 is the central angle. And then they say 2 times the measure of PRQ, because PRQ and PQR are both equal. So they set that up and they have to equal 180 degrees. And then you just use some basic algebra here, subtract 45 from both sides, and then divide by 2, and you get the measure of those base angles, or each measure 67.5 degrees. Okay, a couple of things there. Remember, all radii of a regular polygon are congruent. It's actually very important. Therefore, the central angles divided by a regular n-gon into incongruent isosceles triangles, side, 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 with incongruent vertical angles. It's what I was just talking about with the n, the 360 divided by n. That's kind of where they get that concept from. All right, here's a good theorem to get down. The radii of a regular n-gon, again, n-gon means any number of sides, divide the polygon into incongruent isosceles triangles and can form congruent central angles with the measure of 360 degrees divided by n. Again, this formula right here, 360 divided by n, is a formula I've already explained to you guys and already shown to you guys. If you have a 10-gon, then it can be divided into 10 sides, or 10 triangles, congruent isosceles triangles, and you would say 360 divided by 10 equals that will give you the central angle. If there were 12 sides, it'd be 12 isosceles triangles. It'd be 360 divided by 12, and that would give you the measure of one of the central angles. The area of a regular polygon is 1/2 the product of its apothem and the perimeter. A equals 1/2 AP. This formula is extremely important. Write it down. This will work with any regular polygon. This is how you find the area of any regular polygon. Again, the capital A means area, equals 1/2. Little a is the apothem times the perimeter. So you'll have to know the perimeter and you have to know the apothem to find the area of a regular polygon. Let's take a look at example 2. Find the area of the regular octagon. Okay, so in order to figure out the area of a regular octagon, we have to remember the formula A equals 1/2 AP. I start there immediately. So there's 2 pieces I have to have. I have to have the apothem and I have to have the perimeter. Well, if this is a regular octagon, you guys can see that this length of this side is 10. Well, that means all of the sides have to measure 10 because, again, the word regular means they're all the same in length. So to find the perimeter, I simply need to say 10, which is the number, the measure that it's equal to, times the number of sides that I have, which would give me 80. So that would give me the perimeter. So I could plug that right into the equation for P. I also need to solve for A. Now in this case, the problem already gives it to me. You guys can see right here, that is the apothem. So I can plug that into my equation. A equals 1/2 times 12.1 times 80. So you punch that in your calculator and you get your answer, and you've solved for the area of the regular polygon. Of course, remember your units here would be centimeters, in this case squared. So that's a very important concept that you need to understand. Here, this one's a little bit different. Okay, so this one's probably one of the more difficult ones that you guys will have to do, but it's not impossible. We just got to look at it and try to figure this out. We're asked to find the area of a regular hexagon. So immediately, what should come to mind is the equation, and it's not on the screen here, the equation A equals 1/2 AP, because it's a regular polygon. The work that you see there on the screen now, the 6 times 4, that's because there are 6 sides to a hexagon. A hexagon has 6 sides, and each side here measures 4. So that would give us 24 inches for the perimeter of this shape. We also know that the measure of PQ or PCQ is 60 degrees. PCQ is this angle right here. If you guys hopefully remember, this is called the central angle. The central angle measured 60, okay? So that's 60, and we also know that this angle P and angle Q both have to measure the same measure because we have an isosceles triangle here. Well, if you do the math on this particular one, you'll find out quickly that they both have to be 60 degrees. Now, the reason that's important is because that can help me figure out the length of some of these sides. CP and CQ have to be equal because they're both radii, and then PQ, which is the base here of the triangle, the base here right here is PQ, that also has to be equal to, that's equal to 4, because we already knew it was equal to 4 because of the 4 inches here. But if all them angles are measure 60 degrees, then we know that this has to be 4 and this has to be 4 because all of the angles are 60 degrees. So we have an equilateral triangle here. And by doing that, what we can do is we can figure a couple of things out. Because I know that PD, the apothem, it also bisects the side. So if the whole piece here is 4, then the two pieces have to measure 2. So that's where they get DQ is equal to 2 inches. So hopefully you guys can see how I can figure out what A is. I'll kind of draw it to the side here so we can really see what's going on. This is 4, that's the radius of the circle, or in this case of the hexagon, and then it's a right angle, and then this is 2. So hopefully you guys can figure out, hey, I need to use the Pythagorean theorem here because this is a right triangle and I'm trying to find one of the missing pieces. So you go ahead and do that, and I'm sorry that the screen's not displaying it properly, but when you do that, you get it's 2 square roots of 3. So this would be equal to 2 square roots of 3. The reason we have to have that is because that, again, is the apothem. This piece is the apothem. So now I can use that information and plug it into my formula to find the area. And you can see here on the screen that's what's done, and you end up getting 24 square roots of 3 inches squared for your answer, which is approximately, if you punch it in a calculator, 41.6 inches squared. So that's the key concept and crucial component to this. Relationships in regular triangles. Here we're talking about specifically regular triangles. A is going to be equal to 1/3 h. A is the distance. You can see it in the picture here. That distance right there. That's 1/3 h. And then A is going to be equal to the square root of 3 over 6. And the radius is going to be equal to the square root of 3 over 3. It's just showing some relations in an equilateral triangle, because again this is also, it's a regular triangle, so all the sides have to be equal. Okay, that'll come in handy on a couple of your problems that you'll be working on. Your homework tonight is to go ahead and complete numbers 1 through 20 in this lesson. Again, that's 1 through 20 from this lesson. That'll help you get some good practice with this. Just don't get too rushed or too confused with the concepts. A lot of it is going to go back to the comprehension of the key concepts, which was the 360 over n. That's one formula you have to have written down. The area is going to be equal of a regular polygon as 1/2 AP. Those are key concepts that you have to know in order to be able to be successful in the lesson. So I hope you do well. I'm sure you will. Everything should go well with that, and I'll teach you the next lesson tomorrow morning.